Right, so year 12 further mathematicians, we've split this bit before exercise 5b into two parts. The second part of it, and I promise I won't ramble on. So we're going to look at the elastic potential energy in a stretched string or a stretched or compressed spring. Okay. Now, we've already said that the work done by a force, if the force is varying, we integrate the function that defines the force with respect to x between two values. So that means that when the force is lambda x upon L, and we had that as the modulus of elasticity and the natural length, if the function is linear in x, if you integrate that with respect to x, x is the only variable there, x squared over 2, you get lambda x squared over 2L. Now that's going to be the confusing bit. You've got lambda x over 1L, but in the EPE equation, you've got lambda x squared over 2L. And then in a similar way, if you're given the stiffness rather than lambda upon L, kx with respect to x integrates to give kx squared over 2. Right. Crucially, if you're integrating between two values, x1 and x2, you'd use those as limits, and that doesn't change whether you've got lambda and L or you're replacing lambda over L by the stiffness, which is the K. The principle of conservation of energy will tell us that if you consider all the forces, inputs and outputs, work done, etc., everything balances. In the absence of resistances or driving forces and things, we're going to say that if you add the GPE to the EPE to the KE, for any particular piece of motion, that's going to remain a constant, which means if you know the initial total energy, you can work out the energy any other time or balance that. It's a principle of conservation of energy, and they call it principle of conservation of mechanical energy at other times. I think I'll take a photograph of that and I'll attach that to the slides as well. So if we look at, I'm just going to look at examples 5.10 and 5.11, and you can look at the simpler ones, and that way I'm not going to be speaking for half an hour on this. So worked example 5.10, one end of a light string of natural length 0.8 meters, natural length 0.8 meters, and modulus of elasticity 50. Modulus of elasticity 50 is attached to a fixed point O. Attached to a fixed point O, particle of mass 1.5 kilograms is attached to one end of a string. It's released from rest and falls vertically. It's released from rest, it falls, assuming no air resistance. Okay, so we can use no air resistance. We can look at how all the energies relate to each other. At the total energy stays constant. Find the extension of the string when P is at its lowest point, the acceleration of P at its lowest point. Right, so how are we going to do that? So it falls this far, and when it's fallen that far, it will have fallen 0.8 its natural length plus a bit. So those two things will add up to that. At its lowest position, well, that's where it stops. At lowest position, it stops. That implies V is 0. Okay, that's going to be important. So if we then have principle of conservation of energy, which is linked to work energy principle. We've got that at the beginning, let's say that's 0 GPE. At the beginning there was only GPE because it wasn't moving and the string was slack. At the bottom it's not moving, there's no KE. It's at that level, so there's no GPE. It's just stretch and spring. What I'm saying is we can say that that initial gravitational potential energy can equal the final elastic potential energy. Two unknowns in the moment. How are we going to cope with that? So we've got M, we've got G, and does it tell us what value to use for G? I'm going to use 9.8. And the height is 0.8 plus x, which is equal to lambda 50 times x squared over 2 times 0.8. And that looks like it is a quadratic equation. So all I'm going to do is I'm going to work out all those coefficients. So as if by magic, use the calculator, I get that. Quadratic, on these papers nowadays, you reorganize it and we type it into the calculator. So that's menu, equations, polynomial, degree 2, so 31.25 minus 14.7 minus 11.76 and 0.89 and minus 0.42, which we can discard because it doesn't have any relevance as an extension. Right, I'm just going to give the dog a treat. So we get x is 0.89 meters. The question wants the acceleration of p at its lowest position. Right, I can't do it without drawing a diagram now. So at its lowest position, we've got the particle at the end of a stretched string, but it's still got a weight, okay? So it's stopped moving, but remember, that force has been growing and growing and growing, so it's now, and it's been slowing it down. This force is bigger than that force. It's not in equilibrium. As it's been slowing, it's been accelerating this way. Even though it's stopped, it can be accelerating. Okay? So that's the diagram. Newton 2 upwards. T take 1.5 G is 1.5 A, and T is lambda x over L. Elastic potential energy, x squared over 2L. Hooke's law, the tension is that without the 2 in it. So we've got 50 multiplied by an extension of 0.89 0.8922. That explains why the calculator uses it. A bit sneaky, that, isn't it? So 0.8922 all over L, which is the natural length, got to be in meters. Take 1.5 times 9.8 is 1.5 times A. Work that out, divide by the 1.5, and you get 37 meters per second squared. Right. Perhaps important to note that when we do some of these questions, we're going to have a natural length. There will be another point where the tension and the weight are in balance, which will be an equilibrium position, below the point at which the string starts stretching, and then beneath that will be the point at which the object stops falling. Next year, we're going to talk about things oscillating around that point, but not this one. And already I'm saying too much, right? So that's, and I'll photograph that and attach that to the notes. The other one I wanted to do was this one here, light elastic spring. So this is 5.11, natural length 20 centimeters, 0.2 meters. We're not falling for that trick. The mass is 0.8 kilograms, rests on top of the spring, which is in equilibrium. So that's the natural length of the spring. In equilibrium, it sits in that position. Part A, find the modulus of elasticity. Right, so a diagram. If it's on a spring, sat on a spring, there's a thrust upwards from the spring on the object, and it's got its own weight, 0.8 g. Right, I'm not going to use that pen anymore, it's not working. In equilibrium implies that vertically we can say that the tension is balanced by 0.8 g, so lambda multiplied by, right, let's work out this extension properly. It should be 0.2 meters long. It's 0.12 meters long, so the compression is 0.08 centimeters over a natural length of 0.2, and that's equal to 0.8 times 9.8. When you work that through, what we've got, oh, we want an answer in terms of g, so let's put the g back in. 0.8 g over 0.08 times 0.2. Well, that cancels with that to give 10. 10 times 0.2 is 2g as required. Right, this next bit's a bit more complicated. So the spring is pushed down a further 3 centimeters. So initially, compression, so we might use compression x is 0.3 added to the 0.03 added to that, so it is 0.011 meters. Okay, so it's compressed .11 meters from its natural length. If that was the equilibrium position and it's pushed further down, it's going to spring up. We're looking for the maximum speed of the sphere in the subsequent vertical motion. So the work energy principle says that at any particular time, GPE plus the EPE plus the KE is constant. So initially, it's at rest, therefore the K is 0. Let's also assume that point is where the GP is 0, and assume GP is 0. So this constant here that constant bit will be the elastic potential energy at the beginning, which is going to be lambda x squared over twice the natural length. And then at a general, so what should we say? Should we say a general height above that? General x, a general height. We're looking for this compression to work out the elastic potential energy. Let's call that x. That's going to be that compression take the height it's moved through. This might require thinking about again. So at any other point in its motion, we're going to get a GPE, which is mass, multiplied by mgh plus an elastic potential energy, which is going to be 2g multiplied by x squared, we'll come back to that, over 2 times the natural length, which is 0.2, plus a kinetic energy, which is half times mass times v squared. Right, where on earth are we going with all this? That has a value. Work it out. I'm going to believe the book and believe that it's 0.5929. At the moment, we've got h's and x's. Since we want the maximum speed of the sphere, I want to set it up in terms of one or the other. I think I'm going to write, since there's an x squared term, I'm going to write that in terms of the x. So we're going to get 0.8 times g multiplied by the height is 0.11 take x. What's this going to cancel to give? We've got 2 divided by 0.4, 2 divided by 0.4 is 5. Oh, of course it is 5g x squared plus 0.4 v squared. A horrific looking expression, but we can turn it into an expression for v squared in terms of a quadratic. And this is what the book does. Okay? The book expands all that and then rewrites it as v squared is minus 122.5 x squared take 0.16 x take 0.67375. You may want to check you can rearrange that to get that. Why have they done that? Because one way of finding the, notice we've now got v as a quadratic in x. They've chosen to complete the square to find the maximum value. Is there another way to do the same thing? What happens if we differentiated v squared with respect to x? So we've got double that value is minus 2. Oh, mine's going 122.5 times 2 is 245. So minus 245 x plus that times that, 122.5 times 0.16 is that, which happens to be 2g, when dv squared dx is 0, we get a max, which is when this is 0, so when x is 19.6 divided by 245, 19.6 divided by 245, oh, 0.08 meters, 8 centimeters. Oh, that's better than completing a square. Completing a square is just painful, isn't it? And then put that value back into this to get their expression. Right. Key bit's there, and already I'm talking too long. A sense of looking at equilibrium. In these vertical examples, tension equals the thrust equals the weight, or hanging downwards, the tension will equal the weight. It's this idea which is the crucial one. And given, look at the starting point, it was at rest at the starting point which gave us the value of this side. And then everything else was written in terms of a general position, a general x, to give us that. Right. 2 lessons this week, and then, well, I don't know, next week might be, we might find suddenly we're back in and chatting again. So, that's the A2 work. We don't have to worry about that this year. 18 questions. I'm going to finish this by 25 minutes. We've got 35 minutes to watch the video again. Try some of these, knowing that we're going to use the other hour this week to spend more time on those. Or you could ask me about the ones from before, couldn't you? Right, good luck with those.